All right, so 12.2, we're talking about vectors now. And technically, the majority of what we cover in this section is supposed to be review. Vectors are something that are generally covered in trigonometry or a pre-calculus type of class. But usually in those courses, we restrict our attention to two-dimensional vectors, or vectors in two space. And here, we're going to be looking at vectors in both 2 space and 3 space, with a very brief mention of higher dimensional vectors. So for that reason, we do have a lot to cover here, but I'm going to go through a lot of the terminology and things that are supposed to be reviewed somewhat quickly, just so we can focus more on the new stuff. So let's begin with what a vector is. A vector is a quantity that possesses both magnitude and direction. At least that's the way that we choose to think about it in this class. If you go on and you take linear algebra, or if you've already taken linear algebra, you know that the definition of a vector is actually much more general than this, but this definition will serve our purposes just fine. So typically the way that we represent vectors is by using an arrow. You have a couple of examples down here, this v and u here. The magnitude of the vector is it corresponds to its length. So whatever the length of that vector is, that's how we define its magnitude. The direction is given by the direction in which it's pointing. And we'll kind of give more accurate ways of representing magnitude and direction a little bit later. Now, both of these vectors here, you see there's an A, B here, and a C, D here. If these vectors live in either 2 space or 3 space, we can associate points in space with the endpoints of this vector. The endpoints are called the initial and terminal points of that vector. The initial point would be like this point right here. The terminal point is the point where the arrowhead appears. Okay? Now, vectors are used for all sorts of things in the sciences, in physics and engineering, etc. But in many of the applications that we're going to be looking at throughout the course, vectors are meant to represent things like forces. Forces oftentimes have a magnitude and a direction associated with them, or they may represent displacements. If I take an object and move it in a straight line from A to B, the magnitude of that vector might represent how far the object traveled, and the direction tells me the direction in which it traveled. So displacement is that idea. Vectors can represent either of those things, and they often do. We have a couple of different ways that we notate vectors. You'll notice here we use bold, lowercase letters oftentimes to notate a letter or a vector. Other times, if we want to call attention to its initial and terminal points, we can use this notation. So in this case, if you have a vector with an initial point of P and a terminal point of Q, we can notate the vector as PQ with an arrow over it. The arrow should be pointing towards the terminal point, Q in this case. If I had written QP with an arrow over the top, then that would be a vector with the same magnitude, but it would have reversed the initial and terminal points. So that means that the order that you write these letters in matters. Okay? Now, a really important aspect of vectors is that is what it takes for 2 vectors to be equal to each other. Again, we defined a vector as a quantity that possesses both magnitude and direction. It doesn't say anything about their position in the plane or their position in space, depending on where these vectors live. So as long as 2 vectors have the same magnitude, which would indicate we would find by comparing their lengths, and the same direction, where's the arrow pointing, then those 2 vectors are considered to be equal, even if their initial and terminal points are not the same. So in this case, vector v appears on this part of the page, vector u appears on this part of the page. They're not in the same position. They have different initial points and different terminal points. But if we were to compare their magnitudes, their lengths, they would be the same, and their directions, they're both pointing in the same direction. So for that reason, we would say that v and u are equal. We consider these 2 vectors to be identical to each other, even though they're in different positions. And that's a really, really important thing to start getting your mind around when working with vectors. One vector in particular, excuse me, we single out and we give it a special name. It's called the zero vector. The zero vector is the vector whose initial and terminal points are the same. If you could imagine taking this point B and bringing it down here until it collapsed down to point A, then we would have what just looks like a single point, and that's the zero vector. The zero vector has a length of 0 because it's essentially just a point, and it's also directionless. It's the only vector that doesn't have a direction. Okay? Now, kind of, again, moving quickly through this, moving forward, what can we do with vectors? Well, vectors, if we think of them as quantities, we want to be able to perform operations on them. And we're going to go through the valid operations that you can perform on vectors next. So starting with addition, what does it mean to add two vectors together? Well, we use something that a lot of people like to call the tip-to-tail technique. If I wanted to find the vector u plus v, where u and v are vectors, then what I do is I take the initial point of v, so if you can see v here, here's its initial point, and I basically stack it on to the terminal point of u. I make it so that this initial point for v and the terminal point for u coincide, and in that sense I'm sort of connecting these two vectors. And then I take the initial point of u in the position that I've placed it in, and the terminal point of v, and make that the initial and terminal point of this sum here. So u plus v is this new vector that I create by using this tip-to-tail technique. That's a rational and reasonable way to define addition because of what we want addition to represent in a physical context. Let's think of these as displacement vectors, for example. If I take an object and I move it from this point to this point, then u would represent its displacement vector. But then, if after moving the object to this direction first, if I change direction and move the object from this point to this point, then v becomes the next displacement vector. So if I want the net displacement, if I want to determine what the net effect of those two motions was on this object, this red vector, u plus v, connecting those two, represents that net displacement. I started here and I ended here. So that's kind of how we think of sums of vectors in applications. It's the net effect of the two vectors that are being added. This particular representation here of the sum of u plus v is oftentimes referred to as the triangle law because it creates something that looks like a triangle. We also have another way of looking at addition, something called the Parallelogram Law, which is what happens if you redo this addition in the other order. So notice here, if I do u plus v, then u plus v would be this red vector. It's the same picture that we have here showing up here. But what would happen if I reverse the order of addition? Instead of u plus v, what if I do v plus u? Well, v plus u literally means that we start with v, so instead of going along u first, I would go along v first, and then I would take the initial point of u and have it coincide with the terminal point of v, the way that we see here. And if you notice, because the u's here are parallel and the v's here are parallel, it creates this parallelogram. And the net displacement here takes me from the same initial point to the same terminal point as when I did u plus v. What does that mean? Well, what that tells me is that u plus v and v plus u are the same vector. They're equal to each other. What that means is that addition with vectors is commutative. You can reverse the order of addition and you still get the same result. Okay? Now, in a physical context, in physics and engineering and things like that, we oftentimes call the sum of two vectors a resultant vector, so you may hear me use that term here and there. I just wanted to throw that in just so there's no confusion there. So that's one operation that we can perform on vectors. Let's look at the next one, something that we call scalar multiplication. In the context of vectors, whenever we use a real number, we refer to real numbers outside of vectors as scalars. And it's possible to take a vector and multiply it by a scalar. Those are two different objects. You multiply a real number to a vector. But what does that literally mean in the context of these arrows that we're drawing? Well, if you have some vector v, and if you have some positive scalar c, then the vector c times v is the vector whose magnitude is equal to the magnitude of v times c. So for example, if c is equal to 2, then that would double the length of v. We see that happening here. If this is v, then 2 times v is doubling its length. 1/2, if c is equal to 1/2, and that would cut the length of v in half, for example. Okay? So that's the reason why we call these things scalars. It's because it scales that vector. Now, also important is the fact that multiplying a vector by a positive scalar like this doesn't change its direction. It only changes its magnitude. All three of these vectors here are pointing in the same direction. They've just been scaled up or down. Larger or smaller is probably a better way to say that. Okay, so far we've only dealt with positive scalars, but what if a scalar is negative and we multiply that to a vector? What does that do? Well, if a scalar is negative, it does essentially the same thing. It scales the vector by either enlarging it or shrinking it, and the negative part of that scalar has one additional effect. It flips the vector around so that it points the opposite direction. So for example here, negative v, which I'm going to mention on the next page, is interpreted as -1 times v. -1, if you take its absolute value, is just 1, and 1 times v shouldn't change the length of v. So we have the same length, but the negative reverses the direction of that vector. Instead of pointing this way up to the right, we're pointing down to the left. If you multiply by something other than -1, but still negative, the negative will still flip the direction of the vector and then scale it by a factor of whatever the absolute value of that scalar is. So this vector, for example, is 1.5 times the length of v and pointing the opposite direction. Finally, if you multiply a vector by the scalar 0, the real number 0, then the result is the 0 vector. And that makes sense because the magnitude would shrink to 0, and that would give you a point. That's what the 0 vector is. All right. Let's talk about subtraction next. Vector subtraction, we actually interpret... Oh, I'm sorry. I'm getting a little bit ahead of myself. There's one term that I wanted to mention here. We talked about this already, the fact that -1 times a vector v, we can simply write as -v, but we literally mean this when we write that. One thing that I did fail to mention, I want to make sure I mention this here. Any pair of vectors that have either the same direction or opposite directions are called parallel. And in that sense, even if two vectors are exactly equal to each other, we still call them parallel. It's a little bit different than how we think of lines. If two lines coincide, we normally wouldn't call that parallel, but with vectors, we can call them parallel that way. All 5 of these vectors down here in this previous example are parallel to each other. And that's really important. When you multiply a vector by any scalar other than 0, whether it's positive or negative, the resulting vector will always be parallel to the one that you started with. Okay, so let's come back over here. How do we deal with subtraction? Well, we define subtraction in a way that you can define subtraction for real numbers. If I have two vectors u and v, then by definition u minus v is equal to u plus the opposite of v. That would be true if u and v are real numbers. We can think of subtraction as simply adding by the opposite of something. But here we have a different meaning behind what opposite is, or what negative v is. So let's take a look at that graphically and see what we're up against here. So suppose we wanted to subtract u and v, u minus v specifically. This image kind of shows you what that would look like. So first of all, take a look at this. If u and v, instead of being put tip to tail, if you have both of their initial points coincide, so that they kind of both point outward from that initial point like this. We have u and v sketched out. Now, this definition for u minus v requires that we don't add u and v together. We need to add u to negative v. Well, the point of having v point this direction is so that I can see where negative v would point. Here's negative v. Okay? Now, notice, if we want to add u and negative v together, one way of doing that is using that parallelogram rule that we talked about. Okay? So this here creates that parallelogram, and u minus v would be that diagonal of that parallelogram. So this is a little bit complicated. It's not quite as simple to see how u minus v relates to just u and v in the first place. But again, remember, you can take a vector and move it around in space or in the plane, and as long as you don't change its length or direction, you're still talking about the same vector. So what if I picked up the vector u minus v, this red vector right here, and shifted it up here so that its initial point coincides with v, and the terminal point of v, and its terminal point coincides with the terminal point of u. And then if I ignored everything else down below here, I would get this picture right here. And what this does is it shows us how the difference between two vectors geometrically looks like a triangle. If I have u and v coincide so that they have the same initial point, then the difference of u minus v will be a vector that connects the terminal points of u and v, but points toward u, points toward the first vector in that difference. Okay? That's an important way of understanding subtraction. We're going to use that interpretation in the next section when we talk about the dot product and relate that to something from trigonometry called the law of cosines. That's going to come up later. All right. Trucking along here. So far, all of the work that we've done with vectors has been dealing with them in a strictly geometric sense. We've only been looking at them as arrows kind of floating around in empty space, right? But typically when we're dealing with vectors, it's much more helpful to impose some kind of coordinate system on them. So if a vector is two-dimensional, we can put it in the plane somewhere, the Cartesian plane. If a vector is three-dimensional, we can put it in our three-dimensional coordinate system that we introduced in the previous section. So let's think about that for a moment. Here, in this picture, we have several vectors that are all equal to each other. All of them have the same direction and the same magnitude if we compare their lengths and direction. So even though they're all the same, they appear in a number of different places in the plane. And what we need to do is determine a way of labeling that vector so that it says something about its position in the plane. And the way that we do that is by using something called components. So the benefit of having a coordinate axis is we have coordinate axes, is that we have two axes, in this case, three axes in three-dimensional space, that we can use to measure quantities. Now take a look at this vector right here. I can break this thing down into a horizontal component and a vertical component, going from its initial to its terminal point. Using the grid, I can see that the horizontal component has a length of 3 and the vertical component has a length of 2. Those components are measured relative to the x and y axis. When I say horizontal and vertical, what I really mean is as I go from the initial point to the terminal point, what is my displacement in the direction of x? What is my displacement in the direction of y? So because the displacement in the direction of x is 3 and the displacement in the direction of y is 2, then I can call this vector 3, 2. This is called the component form for that vector, and that's what those numbers represent. How far do I move in the x direction and how far do I move in the y direction from my initial point to my terminal point to create this vector? All of these vectors, even though they all have different initial and terminal points, they all have the same component form, 3, 2. Okay? One thing I do want to mention about component forms here is what if I had something that pointed like this direction? Okay? As I go from my initial point to my terminal point, I'm moving towards the right. Let's just say that that's 5. And then I'm moving down. In component form, if we move down, we interpret that as being a displacement in the negative y direction. So I would give that a negative component to signify that. Similarly, if I move to the left, I would think of that as a negative x component. In component form, this vector would be written as 5, negative 2. It's important to see that because you need to know that components can be negative and they represent something specific. Okay? All right. So again, these angle brackets here are how we know that we're looking at a vector in component form. I do want to mention something just briefly here. A lot of people taking Calculus 3 are either simultaneously taking linear algebra, or have taken it, or will take it very soon. And there's a lot of overlap between Calculus 3 and linear algebra. One thing that you have to be careful about in linear algebra, we also talk about vectors in 2 space and 3 space, but for their component forms, we don't use angle brackets. We use regular parentheses as if they were points. And the reason we do that is because in linear algebra, the angle brackets are reserved for something else. They mean something else in that course. Specifically something called an inner product. We don't deal with inner products in a general sense in this class, so we don't make that distinction. But there's something to be careful about, especially if you're taking that course at the same time as this one. Okay. Now, just like, or coming back to this picture, we had that same vector 3, 2 appearing in all these different positions, but notice one of these positions puts the initial point at the origin. And something convenient happens when we do that. If the initial point of a vector is placed at the origin, then the terminal point will look exactly the same as the component form for that vector. Notice here this terminal point is the point 3, 2, and we know that the component form for that vector is 3, 2. That only happens when the initial point of your vector is the origin. And because we really like that, there's a lot of times where we want a vector to be positioned that way. We call vectors that have their initial point at the origin position vectors. Here's an example of a position vector in 2 space. You can see the initial point is at the origin. Here's one in 3 space. Again, the initial point is at the origin. Okay, and in both cases, the terminal points of those vectors, their coordinates look the same as the components of that vector in component form. Okay, I'm going to go ahead and wrap this video up here. We'll pick up where we left off in the next one.